Right, next, contextual validity of reports. So we have our work report context. This I covered a bit earlier in a very fuzzy way. I'm going to go into a bit more detail now. Right, so this is the set of all contexts, and we're also going to specify here the set of all work package hashes of the work that is coming onto the chain. X is our context, P is our work package hashes. We're going to check that they're all sensible. There must be no duplicate work package hashes, so we're going to make sure that the cardinalities are the same. It's pretty simple. Next, we're going to make sure that the anchor block is known. This is a very strong contextualization for a work package, and therefore a work report, because the context is passed from the work package into the work report. We're going to make sure that this anchor block is within H blocks. I think H is 6, maybe. It's small, right? And it makes sure that it's not very old. So when you author a work package and you choose the block hash, you inevitably are going to choose the most recent block hash to make it most likely to be valid by the time it gets on chain. And this must be not so old that it's passed out of our recent blocks and into the depths of history. So this is what we do here. For all X's in the contexts and for all Y's in our recent block information. For all X's in context, there exists a recent block that matches our anchor block, whose block hash matches our anchor block. Yeah, we know about the anchor block. This is what it's saying. We know that the anchor is in recent history. This essentially just ensures work packages don't stay valid indefinitely, or work reports don't stay valid indefinitely. You have to fix them in time. You don't have to fix them to a specific block that they can get introduced on, because of course you don't know what that block is before it happens. But you have to fix them to an anchor point, and then whatever block when they go on chain, that anchor point cannot be too old. Yep. What is S? Just look at the L time slots. No. Okay, so XB. Right, so the Ketchak. Yeah. Okay. Right. Yes. So XS. So when we construct a work package, which is where this context comes from, we also introduce two important items beyond the anchor block. We introduce the state root of that anchor block, the posterior state root, and the beefy root of that anchor block. Yeah, so we have a state root and a beefy root. Both of these must go into the context and be valid. Why? Because it's really, really useful for that to be fed into the work package, for that to be known at the time that the work package is executed. This allows us to oracleize data back up from the state of the jam chain into basically the cause, right? The working, where the work packages are actually executed. It allows us to get information on the state in core. Now, it's not going to be super, super, super low latency because it could be up to whatever, H blocks old, but it will be reasonably recent. So it means that we're going to be able to look into a reasonably recent state tree. And if we happen to be dealing with something on like something that happened, some bridge thing, then we can also look into beefy. That's what this B is. So XB is the beefy root, and what we're looking for here is the Ketchak hash of the Merkle. I think M is the Merkle encoding of the beefy root in Y. Is that right? I think it's right. We'll have to check this. But anyway, this is a serialization. I think there's like a particular serialization that we're identifying with the M, but it's a serialization. So we're serializing. Actually, that's right. It's the mountain range serialization. So YB. This is in the recent blocks. For every recent block, we store the Merkle mountain range, the beefy Merkle mountain range. But we store it as peaks. We don't store it as the hash of the peaks. We store it as each individual peak so that we can easily add onto it in later blocks. Yeah? If we only stored the hash of the peaks, we wouldn't be able to add onto it anymore. So it's the peaks of a Merkle mountain range. We then serialize those peaks, do a Ketchak hash on them, and that should be equal to the beefy root in the context. So we're going to check the context for the right beefy root, we're going to check the context for the right state root, and we're going to check that we know about the anchor block. Next, we have a secondary anchor point. This is a bit of a subtlety, and it's to do with data lookups. We basically need a secondary anchor that is not recent. It can be quite old, but it needs to be within a certain period. In fact, the period is L. Basically, it needs to be within the auditing period. So I think in JAM, as of now, the auditing period is 8 hours. So L is like 8 times 600. 4,800. So we want the lookup anchor block number to be within 4,800 blocks of our anchors time slot. That's given by HT. Good. Actually, it's not of the anchors time slot, sorry. It's of the current header time slot. So current header time slot, subtract that, and the time slot of the in the context has to be greater than that, or equal. In addition to this, we also have a bit of an ancestry thing. So this isn't something that can be checked on chain, so it's kind of an honesty thing. We're kind of hoping that nodes will check it. But of our ancestors, all header hashes of our ancestors, we want to make sure that we know about this historical lookup anchor, and that it is indeed at the right time. So you have to give the lookup anchor time slot and the lookup anchor header hash. And this is sort of saying, hey, do you know about this header hash? And if you do, is it at the right time slot? If it is, great. If it's not, technically you should not consider the block to be valid. It's possible that a node doesn't have this history available and will just shrug its shoulders and say, nah, whatever. It's not a particularly big deal, but it's better if nodes check, if they can check. Right. Yes. So obviously, a work package of the report shouldn't be the same work package that has been of a report made in the past. Yeah. So you can't take the same work package, make 2 reports with it, and put them both on chain. We retain the reports in recent blocks. So we go through all of the recent blocks, all of the reports in the recent block. Actually, sorry. We go through all of our new reports, all of our recent blocks, and make sure that none of our reports are in the recent blocks. Yeah. Easy enough. Right. The prerequisite work package. Now, as I mentioned earlier, we can specify prerequisite work packages. And we have some sort of formal requirements here for prerequisite work packages that, for all work packages that are coming on the chain, that do not have an empty prerequisite work package hash, then make sure that basically it's in our recent blocks. It's a work package that has made it in a past block, like in one of the last 7 blocks, however many we keep in beta, the recent blocks. If for whatever reason it's gone off the end, it's too old, it's not in beta, it's like you just have to re-author the work package. Yeah, we're not going to make too many affordances for this. In reality, it's not actually that useful, because although you can prevent a work package from being, if you have like a prerequisite, so if you have an ordering to work packages, although we can prevent the second work package going onto the chain before the first work package, what we can't do is ensure that it doesn't become available and accumulated before the first work package. It's possible that the core that the first work package is on isn't available. Like its guarantors are just really bad at sending the things out. They've got bad networking or whatever, and yet the core that the second work package is on has good networking. And even though it's submitted later, it gets made available immediately, and we end up accumulating it first. So for where ordering is really important, it has to be managed inside of the service. Service code has to deal with the possibility of work packages coming in not in the order that they would like. But to try and minimize the effort that they have to go to, we provide this prerequisite system. It's possible that in a later version of JAM, this prerequisite system will be hardened and extended to a point where we can actually give solid guarantees on the order of accumulation. Good. Next, 151. So we require that all work results within the extrinsic predicted to the correct code hash for their corresponding service. This just basically means any updates to the code have not yet gone through, right? So the report becomes invalid if we've updated the chains, if we've updated the service's code, and accumulating it would be under a different code to refining. It's pretty simple. Right. Row prime is equivalent to row double dagger, except of course that we are now inserting the new work into row. Yeah. So we have row double dagger, which is row minus any of the bad work reports from the judgments, minus any of the assured work reports, and now we have to add in or aggregate in the new work reports that we have that have come in from the guarantors, guarantees extrinsic. So if we have, so we go through the cores, we keep the core the same. If we don't have a new item in our guarantees extrinsic for this core, if we do, then it changes to the tuple of the work item, the time that it's gone in, T prime, if you remember, that was the time from before, and the guarantee, the key of the guarantors. I think in reality, this isn't needed. It used to be used in the judgment system, but I think at this point it's not used anymore. So this is likely to go. But at the moment, there you go. That's what it is. That's it for reporting and assurance. So we have our final complete definition of row prime. So we now know how to transition row. We've done all of that. And we are ready for accumulation with big W bold, which is going to tell us what work reports we will be accumulating.